Thank you. I'm Joe Helbley. I'm the Dean of the Thayer School of Engineering, and it's my pleasure to introduce our speaker today and introduce and welcome all of you to today's Jones Seminar. It's great to see such an intellectually diverse audience from across the entire campus, including the medical school here today. For some reason, this is a slightly broader representation than we see at some of our typical Friday afternoon seminars, and it's great to see. So today's speaker, as you all know, is Dr. Eric Mazur, the Area Dean of Applied Physics and the Balkanski, did I pronounce that correctly? Professor of Physics and Applied Physics at Harvard. Professor Mazur earned all of his degrees at Leiden in the Netherlands and came to Harvard as a postdoctoral fellow in 1980.
81.
I aged him prematurely. In 1981, and he's been there ever since, joining the faculty in 1983. He is a highly regarded physicist, a spectroscopist, contributed significantly in nanophotonics and other areas. He's an entrepreneur, having started 2 companies, including Psionics, which is working on developing applications for black silicon, which has been developed in his lab. And he's also a very well-known educator, a pioneer and perhaps the leading developer of peer-based learning techniques, peer instruction, as a way of helping students learn science effectively. He's been developing and perfecting and applying these techniques for over 20 years, and when I met him and had a conversation with him at a reception last summer, he told me that he was about to take the next year completely rethinking his approach and using perhaps an amplification or maybe a departure is the best way to describe it from the pure learning techniques he's developed to try and do even more in helping students learn physics, appreciate physics, and learn physics deeply. I think one of the things that sets his work apart is not just his use of innovative and creative techniques in the classroom, but also his use of scientific data-driven approaches to try and quantify the extent to which students learn differently, and learn better with the flipped classroom, student peer-driven instruction, and other techniques that he's developed. So let me stop there and simply ask you to join me in welcoming Eric Mazur to Thayer.
Thank you, Joe. Well, it's a great pleasure to be here. I visited Dartmouth a number of times. I've spoken here both on education and on my research. I'm always struck by how devoted people are to both teaching and research, which is something that I enjoy doing too, both activities at the same time. I don't think that one is exclusive of the other. So it's really wonderful to be able to talk about something that is very close to my heart, namely the combination of those 2 activities. How can we be more scientific about our approach to teaching? Now, those of you who've heard me speak before about education probably remember this picture. I show it in almost all of my education talk. It's a very old picture of me teaching my physics for pre-med course at Harvard. This picture was taken BC, before computers. See, I'm using an overhead projector there. When I became an assistant professor at Harvard, I was asked to teach the course that none of my colleagues wanted to teach. Right? I mean, these pre-meds are not students who take physics because they want to learn physics. They take physics because they're told to take physics, and they have to take physics in order to be admitted to medical school. Well, having never been trained in teaching, I did what I think most of us do. I emulated the people who had taught me. I taught the way I had been taught. Never even questioned the approach to teaching. In retrospect, that's strange, right? When you do something new, the first question you should ask yourself is, how am I going to do it? But to me, it was totally clear, and it was a hidden assumption. I wasn't even aware of making that assumption, that the way people learned was basically the way shown here. Then years later, I discovered that in spite of my high end-of-semester evaluations, and in spite of my pre-meds being able to solve rather complicated calculus-based problems that I wasn't even sure I would do well on an exam, they actually learned next to nothing. After about teaching for 7 years, I gave them a conceptual survey called the Force Concept Inventory, which tests students' understanding of the concept of force. I'd read about this Force Concept Inventory, and the author, Professor David Hestenes at Arizona State University, claimed that there's very little difference whether you give this conceptual survey at the beginning of a physics course or at the end. The result is more or less the same, and it's not that different from when you put a primate behind the keyboard just pressing random buttons. I looked at it and thought, these are things that I learned in high school. Right? I mean, it has nothing to do with my course. But then I read how it correlated with different teaching approaches. Actually, it doesn't correlate. The gain is 0, regardless of the rating of the teacher, regardless of the approach. When I read that, I felt challenged. I was sure that in my class at Harvard, things were going to be different. But as a scientist, I've learned not to just make assumptions like that and assertions like that. So I thought, I'm going to show that in my class it's different. So I gave it to my students. And we were already in the middle of the semester. It was too late to do a pre-test at the beginning of the term. And as soon as they started, I was dragged out of my ivory tower. Because one student raised her hand and she said, Professor Mazur, how should I answer these questions? According to what you taught me, or according to the way I usually think about these things? Now, that was the moment that I realized that the lecture, and ironically, I'm giving you a lecture now, the lecture is a process that focuses on the dissemination of information, or on the transfer of information. But if you ask yourself, what is education really? Is education just a transfer of information? We live now in an information age. There are many different ways of getting information, so why do we have to transfer information this way? And of course, education is not just the transfer of information. There's a second, much more important process that needs to take place. The learner needs to make sense of this information. So I see education as a two-step process. 1, information transfer, you have to have that, right? 2, making sense of that information, connecting it to your own experiences, having this aha moment, oh, I get it now. Now, in the traditional approach to teaching, in a space like this, where does that second step take place? Ask yourself that question. Is it taking place while you're sitting in a room like this, taking note, listening to an instructor, teaching physics or engineering or whatever? I think, maybe occasionally, if I think back of my own education, maybe occasionally I had an aha moment. But most of these aha moments took place outside of the classroom, either when I was poring over my notes, trying to make sense of what I'd scribbled down, or when I was applying my knowledge in a homework or in another setting. So in the traditional approach to teaching, the focus is on the easy part, the transfer of information. The hard part, making sense of it, is left to the students on their own. So that's when I realized that if you think about it pragmatically, that's not the best thing to do. We should invert this. We should give the students the responsibility for gathering the information, and then use the class to make sense of that information. And that's when I started to develop peer instruction. I won't talk much about peer instruction today, but if you're interested in hearing more about this transformation and exactly how peer instruction works, I'll say a few words about it later. You can go to YouTube, where there's a talk by me called Confessions of a Converted Lecturer, which explain that process. Today we're going to talk about data, and I want to start with some data that I came across a year ago, which sort of backs up some of the statements I've just made. They were collected at MIT. This is a paper that was published in 2010 by people at the Media Lab, who developed a wearable sensor that can be worn around the wrist that measures transdermal electrical activity, which most of the paper is basically devoted to describing the hardware and to show the correlation between the electrical measurements taking place at the wrist and electrical measurements in the brain. That's great because you don't have to put people in electrodes' heads. You can give them this little sensor, and then they can go about whatever they want to do, and then you can download the data and analyze the data and correlate it to the activities that the people were involved in. And there's one graph in that paper. This is not a paper about education, by the way. It's a paper about, neurobiology, if you want, and about electrical engineering, combining neurobiology and electrical engineering. But one graph shows the result from collecting data on an MIT student during a 1-week period. And here's the graph. You see on the horizontal scale, that's the DOI, by the way. Don't have to write it down. You can download my slides later and then just get the paper. So here's time. I don't know why they start at 4 o'clock in the afternoon. Maybe that's when the day starts at MIT. But anyway, it's a 24-hour period on the horizontal scale. And then day 1, day 2, day 3, day 4, day 5, and so on. Now, the color coding and the letters, which are too small for you to read, label the activities. I want to draw your attention to the activities labeled class. The trace goes flat. Contrast that with what happened during sleep. In other words, the students are more asleep in class than they are when they're in bed. Now, in sleep, we know there are a lot of important things taking place in the brain. Memories get consolidated. Things get shuffled around between short-term memory and long-term memory. There's REM sleep and so on. I mean, there's a lot of important reasons for sleep and for consolidation of memories. But if you look at all the other activities, ranging from study to homework to lab, even chores, the brain is more active than in class. There's only one activity. Stop looking at the screen. Think about it. There's only one activity that matches class. Watching TV. Here we go. Watching TV. And of course, people had done studies, over 40 years ago and shown that people are literally in an almost vegetative state when they sit in front of the TV. The reason is very simple. The mind likes to wander, likes to think, likes to, explore thoughts. When you're in front of the TV, there's this constant stream of information. There's no time to think. I'm sure you've gone to a movie about a book that you had read before. And often what you see neither corresponds to what you imagine, nor creates the same emotions and impressions. Simply because when you read, you can pause, and your mind has time to wander. When you watch the movie, it's a continuous stream of information that comes at you. But if you stop to think about it, why would listening to a professor, whether it's medieval studies, or music, or physics, or engineering, why would that be different from watching TV? Again, there is no time to think. There's this continuous stream of information, which at best you can try to record on a piece of paper, but there's no time to confront your misconceptions. There's no time to connect the information that is coming in to the experiences and the mental models that are already stored in your brain. So I was really happy when I saw that. And I'm teaching this year a very different type of course. I'm teaching a project-based course. I'm dying to get one of these sensors and have my students wear them and see what happens. Okay, but enough about bashing the lecture, because today I have a very different message. And if you want to hear more about the ineffectiveness of the lecture, I refer you to that Confessions of a Converted Lecturer on YouTube. The message today is, let's not abandon the scientific message when it comes to teaching. When I joined the physics department at Harvard, I have a joint appointment between physics and engineering. It was a very intimidating place to be, because at that time we had 6 Nobel laureates on 27 faculty. We met for lunch, we still do, about once a week. And during those faculty meetings, which are partially social, we often talk about physics, but also about hiring and about teaching too. And thinking back of those discussions, it's actually shocking to realize that scientists completely abandon the scientific method when it comes to teaching. It becomes purely anecdotal. My students learn better when I do this or that. Or my students like it when I do lots of demonstrations. How do you know they do better? How does liking it better correlate to actual learning? Right? These are all hidden assumptions that you make when you have a decision like that. Now, I like to rub in the face of any colleague who refers to anecdotes when it comes to teaching. I'd like to quote Lee Schulman, who was the president of the Carnegie Foundation, and who once said, "The plural of anecdote is not data." So I think we should ask more the question, what's the evidence, right, when we make a statement? What's our goal? What do we want to accomplish? Do we just want to make students happy? Well, then we need to make sure that we maximize our end of semester evaluations. Or do we care that our students are successful in their later careers? In that case, we need to equip them with the right skills, and we need to measure whether or not we accomplish that. So I am currently treating my classroom as a laboratory. I have my real laboratory, as Joe just mentioned, where we measure the interaction between matter and light. But since I'm teaching, I might as well use my class to gather data about teaching. And I'm going to show you 3 little projects, completely disconnected, pardon me, forward 2 slides here, 3 sort of disconnected projects that show how I can collect data in the classroom and use those to take decisions about how to address certain problems that might occur or how to improve the learning. The 3 disconnected subjects. One is gender issues. The second one deals with lecture demonstrations. And the third one was confusion. And I want to encourage you to ask questions at any time. And I'll pause between the 3 different sections in case you want to ask questions. That's probably better than waiting till the end. So let's start with gender issues. I told you already about the Force Concept Inventory, the FCI. It has been given in many physics departments all around the world. It's been translated in many languages. There are lots of data. But about 10 years ago, at the University of Minnesota, they started to segregate the data obtained from female students and those from male students. And they found out that there was a very statistically significant gap between the scores obtained by women and by men. These are the post-test scores. What are post-test scores? Pre-test means at the beginning of the university or college level physics course. Post-test is at the end of that course. When I saw this, I thought, oh, I better go back to my own data. I'd collected data for about 10 years and see if there was something similar in my course. So I'm only going to plot now the gap, not the absolute values of the data for the female and the male. So that gap there, you see, is about 12%. The 2 courses I taught at Harvard, 2 different level courses, both had a gap that was also very statistically significant. And then I went to some colleagues at Worcester Polytechnic Institute, which is just outside Boston. And they had been using our facility for administering this FCI, and we got their data, and they showed a similar gap. So before I tell you a little bit about what we could do about this gap, let's first ask ourselves, what causes this gap? And here, actually, I do not have any scientific data, so this is still partially anecdotal, but it will get better towards the end. For example, is it cultural? I, as many of you here too, have the benefit of taking sabbaticals, and whenever I'm on a sabbatical, I try to convince my colleagues at the host institution to administer the FCI in their classes. And one of the first institutions I visited after doing part of this, after beginning this study, was National Taiwan University, Taiwan Daishui, in Taipei. The reason I was there was because the whole first generation of my graduate students came from Taida as graduate students, and then went back and eventually became professors. So when I got my first sabbatical in the early 90s, I was invited to spend half a year there. Actually, before I was there, pardon me, I jumped the gun here, because before I was there, I was in Europe, in Belgium, and I had always thought two things. One is, in Europe, we don't have these problems. Neither the low performance on the FCI, nor any gender gap. So I was at an engineering school. I cannot disclose the name of the school because the results were so shocking that the dean called me into his office and said, "You're never going to publish these data or tell anybody about these data." So let's just say it's a good engineering school in Belgium. They speak Flemish in Belgium, which written is no different from Dutch. So I was actually able to translate the FCI into Dutch, right? You don't want there to be a language barrier. We gave the FCI to the first-year physics students, in a first-year physics course at that university. It was shocking. First of all, they were very low, but much more shocking was the incredibly large gender gap there. Then I went to Taida, as I said, and I told my former students who were junior professors there about the FCI and about the results at Harvard, and they said, "Oh, let's talk to our colleagues and see if we can give it at Taiwan Daishui." Well, they said, "We cannot give this here." The older colleagues said, "We cannot give this here. This is too simple. Our students learned this in high school." I said, "Well, I've tried it in Belgium. I've tried it in Holland. Even at Harvard, they're having difficulty with this test." Immediately, their respect for me took a nosedive. No matter how hard I tried, I was unable to convince the people at Taida to administer the FCI at Taida. But luckily, there was a neighboring institution, National Taiwan Normal University, which does teacher training, where they were very interested. So they translated it into Chinese. I had my graduate students translate it back from Chinese into English, just to make sure that no subtleties were lost. And we administered it, and two things stood out. The students, even though these were not Taida, National Taiwan University, sort of the flagship university of Taiwan, National Taiwan Normal University, which is mostly a teacher training college, is by nowhere, as distinguished as Taida. But the students did very well as Harvard physics majors. But more importantly, there was no statistically significant gender gap. Now, here's where it gets a little bit anecdotal. What were the differences? The differences were that in the physics department in Belgium, there was not a single female faculty. It was a completely male faculty. At Harvard, and in the US in general, it's in the 10 to 30%, depending a little bit on the department. In Taiwan, there was gender equity between the two. So maybe that the environment, but I say maybe because I am not 100% sure, I don't have enough data, the environment makes a difference. What about the effect of pre-college education? That I can only do for my own class because I collected data. I asked students to report back on their exposure to physics before. And there was a certain percentage of students who had never had any high school physics. There were students who had just a standard high school physics course, and then a fairly large proportion who had an advanced placement course. And notice that there is indeed some correlation, but nowhere the type of correlation you would expect. The FCI only tests students' understanding of the concept of force, okay? This is what gets covered, quote unquote, in what? The second, third, fourth week of a standard physics course. So even students who get through the AP, and the Harvard students who take an AP physics course typically tend to score a 5, get only about, what is it, 60% of the questions correct. That's on the cutoff between Aristotelian and Newtonian thinker. Kind of shocking, right? These are the data for the female students at Harvard. The male students outscore the men, and there's a persistent gap. In other words, the pre-college education doesn't do much to mitigate this gap. But what is even worse is that the women are underrepresented in the higher levels. You have about equal number of females that have, and males who have not had high school physics. The same in the high school physics bin, but you have far more men, 118 versus 57, who have taken an advanced placement course. So there's not much I can do about that, right? Because that's on the input end. But the question I wanted to ask was, is there something I can do in my classroom to mitigate this, to reverse this trend? And the reason I started to think about this was because the method of instruction that I developed diminished competition and increased collaboration, and shifted the focus from procedural analysis to verbal discourse. And there's been plenty of studies that have shown that women tend to thrive in a less competitive and more verbally oriented environment. So let me tell you a little bit how I switched my teaching, and I'll just give you a very quick overview. I require my students to come now to class prepared. Rather than reading the textbook to them, they either have to read the book before coming to class, sections of it, of course, not the whole book, or watch a lecture of me or somebody else before coming to class. And in class, I teach by questioning rather than by telling. So I'll talk a few minutes. I'll put a question on the screen. I have everybody think in silence. Then they commit themselves to an answer. If it's a multiple choice question, we can use a clicker or consumer devices. Then I tell them, now find a neighbor who has a different answer and try to convince that neighbor of your answer. My classes are not very different from this, 200 or so people. You should imagine complete chaos as students start talking to one another. Normally I would always teach and then write on the board and so on and stop. Does anybody have a question? Anybody? You know how it is, right? Students look down, they don't want to make eye contact, right? If you wait long enough that it becomes uncomfortable, it's always the same person in the front row who raises his or her hand. Most of them do not want to get engaged. Here you have to imagine everybody, in fact, so much that they stop paying attention to me in front of the class. I could walk away, they wouldn't even notice. And what happens is that in just a few minutes, the students who have the right answer, who have the right understanding, teach the students who do not. Imagine you have two students sitting next to each other, Mary and John. Mary has the right answer because she understands it, John does not. On average, Mary is more likely to convince John than the other way around. Right? That's just a force of logic. But, and this is the crucial step, Mary is more likely to convince John than Professor Mazur in front of the class. Why? Because Mary has only recently learned it. She still knows what the conceptual difficulties are that a beginning learner faces. She's likely to know what problems John has. Whereas Professor Mazur learned it such a long time ago. To him, it's so clear that he has no idea what the difficulties are that are in John's head. And I'm sure that might resonate with you, both as a teacher or a student, right? You teach a class, a student comes to you, asks you a question, and you think, this is so clear. What is there not to understand about this? Or as a student, you know that if you had a question, you wouldn't ask your professor because you'd get an explanation that went straight over your head. Instead, you'd ask another person from the class after class. Anyway, so in a sense, I exploit the knowledge that is present in the students. There are lots of tricks that I'm shoving under the rug here and lots of little difficulties. But again, if you're interested in more details about this approach, I refer you to what's available online. The key point is, I had analyzed the learning gains of this approach, which are substantial, but I never separated the learning gains for the male and the female population. So I thought, is the increase in collaboration and the increase in interactivity something that helps address this gap? And to that extent, and it was actually quite easy because I'd collected many years of data on the FCI, so all it meant I needed to do was to go back over my data and reanalyze them. So we're going to compare 10 years worth of data spread out over 3 different strategies, pedagogies. One is traditional lectures. I just lecture as usual. Another one was interactive lectures using the peer instruction method. And then a few years after doing that, I decided to permeate other activities with collaboration too. So not only were the lectures interactive, the assignments were, the discussion sections were, everything was collaborative and interactive. We even taught students to work in a group on the homework. So T, I, or IE, interactive engagement, and interactive engagement plus. So let's look at the pretest on the FCI for the 3 different treatment groups, T, IE, and IE plus. And as you can see, the average women pretest score is about 61 or 62, and there's no variation across the 3 treatment groups. But that makes sense, right? Because they haven't had it yet. They haven't been exposed to it yet. I'm going to remove the pretest data, but that little triangle is going to show the average pretest data for the female students. What about the average pretest data for the male students? There's a little bit of variation, but the sign of variation is such that it only reinforces my conclusion, so that's okay. But if I just average all of the data, I get that red triangle. So the difference between that little red triangle here and the blue triangle gives me the incoming gender gap, which is not under my control. So let's now see what the post-test data are. And notice that there are significant gains in the post-test, right? The post-test in the traditional class, look at this for a moment, the traditional class, the students go from, the female students go from what, 62 or so to a whopping 70, only an 8% gain. Right? That's the difference between the first day of class and the last day of class. And you can see that the interactive engagement increases the students' performance significantly. The male students also benefit from the bigger interactivity, but the gap at the right of this graph actually is no longer statistically significant because the women gain disproportionately more than the men. So everybody benefits, but women gain a little bit more, and we're able to actually erase this gender gap. If you're interested in reading more about this, we published these data in the American Journal of Physics. Let me show you another benefit. I can look at individual students rather than class averages. For example, this here shows a student who had a pretest of 70% and a post-test of 90%, right? So I put on the horizontal the initial pretest score, and on the vertical I put the gain, the difference between the post-test and the pretest. Right? So that means if you start at 70, you could go no higher than this diagonal line, right? You can go to 30. If you start at 40, you can gain 60. If you start at 20, you can gain 80. Okay? So this was actually a relatively high gain students. If I take all of the female students in my class, there are more than there are dots, but the dots lay on top of each other. That's where they are. And here are the men. This is in a traditionally taught class. If I look at the students below the mean, you see that there are more women than men. So there are more underperforming or below average women than there are men. There's a clear imbalance in the traditional class. If I go to an interactively taught class, first of all, you see all of those data go closer to diagonal, showing that everybody benefits. And now, if we take those that lie below the mean, actually at the bottom half, I have the same mean, I think, as I had on the previous graph. There are fewer data points below that in that highlighted area. But you can see that there are more men, more underperforming men than underperforming women. So the points I want you to keep in mind from this first little thing is it seems that there's a gap in the sciences that comes from culture and background, which clearly shows that it shouldn't be there, right? It's something that is artificially introduced. And secondly, and I think this is really the good news, is even if there is a gap, we can do something about it by increasing the interactivity in the class. All right, so that's research project 1. Feel free to interrupt me at any time, or we can postpone the questions till later. Okay, demonstrations. I'm an experimentalist. I'm a physicist. I love doing demonstrations. I mean, what better way is there to show how nature works than just to show it in front? So my classes were a little bit like Walter Lewin's classes. I would go on a rocket car through the classroom, you know, in through one door, out through the other, which was opened by the assistants just before it crashed in the door. You know, always wowing the students. One year they actually forgot to open the door, and I crashed in the door. Or I would, you know, hoist myself up to the ceiling, or I'd have this big, massive ball that was suspended from the ceiling as a pendulum. I would let it go, and it would come back, and you'd hope that potential and kinetic energy keep each other, you know, exactly, keep each other in sync, and it wouldn't be crushed by the ball. Anyway, I did all of these demos, and the students, or shooting the monkey, that was another one, right? I mean, you have a not a real monkey, a stuffed monkey suspended near the ceiling magnetically, and you'd shoot a projectile, aiming the barrel of the cannon exactly at the monkey, but then the moment the projectile leaves the gun, the monkey is released. Even though you are aiming exactly at the monkey, both the projectile and the monkey are subject to gravity, and the most miraculous thing is that no matter how fast you fire the projectile, one hits the other. Now, at one point, I read a thesis by a PhD student at the University of Washington who had interviewed students after taking a one-year introductory physics course. And this shoot the monkey demo was one of the things that one of the students vividly remembered. But a year after taking that course, the student was convinced that the instructor had actually adjusted the aim and aimed below, and that's why the monkey had been hit. I thought that's really interesting that, you know, you can do these demo and then they learn not exactly what you want them to learn. So I decided that I was going to actually study the effectiveness of lecture demonstration. And in order to do that, I carried out 7 demonstrations, and eventually 13, because it was a 2-year study, in 4 different modes. I had 250 students in my class. I broke down the class into 4 groups, and I rotated these 4 groups among these 4 different modes. So the modes are called no demo, observe, predict, and discuss. So one week, this would be no demo. That would be observe, that would predict, discuss. And the next week, it'd be different. And we do the demos outside of the main lecture in the discussion sections where we could, you know, reduce the total number of people attending it. So no demo meant we didn't show the demo at all. That was our control group. Observe, we presented the demonstration in the traditional fashion, telling the instructor to do the best possible job explaining it, right? And even addressing questions, but that's it. Predict, we asked students, before showing the demo, we projected a diagram that showed the demo, and then we asked students to predict the outcome of the demo, and we recorded that with a clicker. And then we did the demo afterwards. And lastly, the 4th group, that was the most extensive one, we gave students a worksheet where at the top there was a diagram of the demonstration explaining what it was, and a space to record their prediction in words. They had to describe what was going to happen. Then we did the demonstration, and they had to describe their observation of the demonstration. And then we asked them to explicitly check a box. My observation did or did not correspond to my prediction. And then we gave students a few minutes to talk to their neighbors and reconcile any differences between observation and prediction. Of course, there's more investment of time as you go down this list, right? No demo, no time. Observe whatever time it takes to do the demonstration. Predict, add another 2 minutes to that. And discuss, add about 8 minutes to that. We followed up by giving the students an online free response test at the end of the semester, typically 1 or 2 months after seeing this demo, where we tested the memory of what they'd seen, and we tested whether they could take whatever they had seen and extrapolate it beyond what they had seen. And then we also gave them exam questions which took the same idea from this demo, but put it in a completely different context. In other words, were the students able to transfer the concept from one situation to another? Let me show you one example, which is this loaded beam demo. 2 scales, a plank lying on top of the 2 scales, and an object in the middle. And of course, each scale indicates half the weight of that object, plus plank. But let's say it's zeroed out was the plank on top of it. A common misconception is that it's not going to make any difference where you put the object because the plank evens out the load. We show this demo in the context of torque so that you have to understand that you not only have to balance the weight, but you also have to balance the torques. So that's the context in which we show this demo. And if you move this to the side, one will indicate the full weight of the object and the other will go to 0. Here's the online test, which comes 2 months later. This time it's numerical. We showed 10 and 10. And then we asked the students, if this block goes all the way to the side, what is the reading on this scale? What's the reading on that scale? And then here's the extrapolation. Suppose we don't put it all the way to the side, but we put it halfway towards the side, a quarter of the total length in. What are the scale readings going to be? So let me show you some of the answers. 24% of the students gives the correct answers, 20 and 0, 15 and 5, and correctly mentions torque. So is able to produce the right the explanation that we consider the correct explanation. Another 38% of the students also give the right numbers, but they don't mention the concept of torque, so it's hard to judge how well they understand the underlying physics. But at least it's the correct answer. 20% of the students says it's independent of the position. 20%. I thought, those must be the one who did not see the demo. But no, I checked. They saw the demo. In fact, some students wrote down, as shown in lecture, it does not make any difference where the block is put. I was so excited. I went to a colleague in the psychology department who I know well, and I said, I just discovered something really interesting, a new psychological effect. And he said, really, what is it? And I described this, and he said, Eric, we've known this all along. I said, really? And he said, yes. Why do you like physics? I said, well, I like physics because I don't have to remember that much. I can think through things. He said, exactly. The brain stores models. It does not store facts. So imagine you are a student who has this misconception, right? You have a plank. It doesn't make any difference. You have that. That's the model that's in your head. Now you come to class, and Professor Mazur does a demo, moves the block, and lo and behold, one of the 2 scales goes up and the other goes down. You have what Piaget calls a cognitive dissonance. You go, whoa, that's not what I expect. Maybe you quickly scribble it down, but you have no time to think about it. Before you have time to adjust your faulty model to the observation, the professor goes on and talks. Oh, incidentally, I should show you. The students who are in this group are mostly in the observe group. They are the students who actually saw the demo but did not have an opportunity to think about it, right? So what happens if you do not give the students an opportunity to revise their faulty model? They will adjust their memory to the incorrect model. And then later, use your class as evidence. Psychologists have known this a long time. I mean, trial lawyers exploit that, right? If you put the wrong model in a witness' mind, you can get people to remember things incorrectly. Magicians, advertisement agencies, I mean, there's whole industries that use this all the time. To me, it was actually quite an eye-opener. 10% of the students only give qualitative reasoning. They don't give, they say goes up and goes down rather than giving an answer. 6% of the students, they don't balance the forces, so all of a sudden the two numbers are no longer equal to 20. And 2% give other incorrect answer. If we break it down, the number of correct answers where I count as correct the right numbers and the right reasoning. So they had to mention torque. Look at the observe mode. Is just presenting harmful? But think of the student who actually wrote at the end of the semester as shown in class. He or she, I don't know, was convinced that it stayed the same and that we'd actually proven it in class, right? So here's an exam question that takes this in a totally different context. Yes?
The other data points are exactly the same, 30%.
Yeah.
Can you comment on that?
I beg your pardon?
Can you comment on the other?
I'll comment on it towards the end when I show you the aggregate data.
Okay.
This is very disappointing indeed that these are exactly the same. Yeah, yeah. Yeah. I'll tell you more, and I'll show you the aggregate data, which is a little bit more, which goes into a little bit more depth than just this one demo. Okay. So let's first, before I get to the aggregate data, let's do this exam question, which is actually the same principle. You have two ropes suspending a plank, and the tension in one of the two ropes is given, but that should immediately lead to the conclusion the other rope is also 150 Newton, and therefore the plank as a whole weighs 300 Newton, but that's not explicitly stated. And then the students were told the point at which this other rope is attached is now moved from Q to R, halfway between Q and the center of the plank. What are the tensions in the two ropes? You may think this is a totally different question, but it's really exactly the same thing. You have to balance torques and balance weights. So how do the students do? Well, 36% of the students, 30 with correct reasoning, give the right numbers, 100 and 200 Newton. But then there are some interesting wrong answers. There are 13% of the students who say 150 and 300, so this plank all of a sudden got a whole lot heavier, as you can see, or 75 and 225. And these are all errors in calculating the torques because they take an incorrect arm for the torque. But then, as I was the one grading this exam problem because I wanted to see how the students did, there was a very substantial number of students who came up with very crazy numbers. 112.5 and 187.5. And I just couldn't figure it out. I figured very quickly out that 112.5 is 3/8, and 300 Newton is 5/8. And then there were also 8% of the students, right, 250. So this is about, 18 students in the class. And then there was 1% of the students who had 112.5, so of 2 or 3 students, who had 112.5 for both. Any idea where those ratios come from? I'm in an engineering department, so I can ask this question, right? I wrecked my brains. And then almost when I got to the end of grading, there was one student who revealed his thinking. Any idea where the 3/8 and the 5/8 come from?
They're just mentally dividing the board.
Very good. They just mentally divide the board in two, right, here between the, right? This part is 3/8 and is suspended by this rope. This part is suspended by that rope, and RQ, of course, also has to be suspended by that rope. And here, RQ sticks out, so it doesn't have to be suspended by anything. These are Harvard students, right? Who would have thought? That shows that, once you understand things, it's so hard to understand the thinking that some students have, right? The curse of knowledge, right? I mean, it's really, unless you study the mistakes they make, which is something we typically don't do, right? When we grade an exam, we go through it. When we see a mistake, we say wrong, and we put it aside and go to the next one. We only read the solutions that are correct from start to finish. One point I want to make through this is that actually we can learn a lot, get a lot of insights into the mistakes that the students make. And unless we're aware of them, we cannot address them. Anyway, so there you see a slightly different trend, because now it's not a multiple choice question with a little bit of text. We can actually analyze the student thinking. And you see that there's a slight correlation with answer. But if you look at the quality of the explanation, there's a very strong correlation with, increasingly interactive demonstration, showing that the extra interactivity leads to more. This was sort of hidden. This was sort of hidden in that other test. You couldn't really look at it. And here, again, the percentages are not that different. If we look for all 7 demonstrations in this first year of the study, and we look at students' ability to predict the outcome, there's a slight increase. But if you look at their ability to explain it correctly, where we put a really high bar on explaining it correctly, right? I mean, they really have to not make any conceptual mistakes. You see also a very strong trend. In fact, if I plot this graphically by using the no demo as a control, you can see that observe creates a slight improvement in predicting the outcome. The predict group is bigger, the discuss group is even bigger, but the quality of the explanation increases dramatically. The students who have just observed the demo do barely better than the students who have not seen the demo. But after just doing a prediction, that increases dramatically. So what was my take-home message from this? My take-home message was that if you do a demonstration and just show it, that's not very helpful. Right? You've got to engage the mind. But by just having them predict, which just takes 2 minutes, you can increase it considerably. I was going to pause for questions, but I see that I only have a few minutes left, and this is the topic I'm most excited about. Why am I excited about it? Because who am I to think that, I can have any impact of education? I mean, already 2,000 years ago, Socrates said, we should teach by telling. Maxwell, in his letters, writes, complains about students memorizing by rote. Feynman, in Surely You're Joking, Mr. Feynman, describes his trip to Brazil, where he gives a talk, and he's completely surprised by the graduate student being able to recite the Hartree-Fock equation. And then he asked them, what does this equation mean? And they don't know. So there have been plenty of people who have been complaining about education for thousands of years. Why has it been so difficult to have any change? And why are we still mostly teaching using an approach that dates back to the Middle Ages? Well, I think part of it has to do with this topic that I'm going to raise now, because in general, instructors are praised for clear lectures, right? In fact, I'm sure that your evaluation is not very different from the one we use at Harvard, and it has an entry. Did Professor Mazur give clear lectures on a 5-point scale, right? And confusion is generally taken to be something discouraging, right? But stop to think about it. How do we learn? We don't learn by just taking information, opening our skull, putting the information in. No. We learn by thinking, how does that work? And then going, oh, yeah, we wonder. You have to wonder. You have to overcome this confusion in order to learn. I think it's best expressed by that saying there, to wonder is to begin to understand. So the question that I want to pose is, does confusion indicate a lack of understanding? And the reason is that I started using in my teaching an approach called just-in-time teaching to get students to come to class prepared. This is the question I want to address. Or actually, I want to address the opposite of this. Does the lack of confusion indicate understanding? That's the question I want to address. So I use this technique called just-in-time teaching, which was developed at the Air Force Academy and Indiana Purdue University and Davidson College by 4 instructors. And it was the icing on the cake for peer instruction. It basically asked students to answer, before coming to class, 3 questions on the web. 2 are content-based and they're difficult, but they're graded on effort, not on correctness. And 1 is a feedback question. Tell us what you found difficult or confusing. I developed a system. I've talked to a few of you who are using Blackboard here to implement it, but the system that I have actually shows the students' pictures with their name and their confusion. So the night before class, I press on a button, I see their faces, the names, and what they found confusing. And I would often see students who said, I was confused about this, that, that. I look at the student, I think, but wait a minute, this is one of the best students in the class. And then I had another student who said, nothing was confusing. And then I looked at the picture, I thought, I don't think this is one of the best students in the class. I pressed on the button, sure enough, this was actually one of the lowest performing students in the class. So I sort of anecdotally, I got the feeling that there almost seems to be an anti-correlation. So I decided to analyze the questions, the first 2 questions on understanding and the last one on confusion. Let me show you an example. Here is, and again, my talk is not about physics, okay? I had physics in there, but it's not about physics. It's really about education. But I have to give you an example. Don't worry if you don't understand the physics. That's not my goal here. Consider the capillary rise of a liquid in a glass tube. How does the pressure at point P at the surface of the liquid compare to the pressure at point Q at equal height? Now, liquids have the same pressure at equal height. That's simply because of hydrostatic pressure. So the pressure here has to be the same as the pressure there. Next question. And this was a course totally aimed at pre-med. We used a book that had actually medical applications throughout the entire book. And in the chapter on fluid, it talked about capillaries. And it also talked about alveoli in the lung, which refers to this, which the second question is connected to. 2 identical balloons are connected to a tube as shown. Balloon B is inflated more than balloon A. Which way does the air flow when valve P is opened? Something very unexpected used. We do the demo. If you open that valve, the little balloon empties in the bigger balloon. Because little balloons are more curved, the rubber membrane pulls in more. You may have known that. If you've ever taken a balloon out of a bag, put it on your lips, the first few breaths that you get in take a lot of effort. But once you have some air in, it goes much more easily. But pay attention next time you blow up a balloon. Why is this important for medical students? Well, the lung has alveoli. They're not really balloons, but they're cavities containing gas, air. And the reason babies born before 20 months of gestation have very little chance of surviving is because they lack a substance called a surfactant, which is a liquid that reduces the pressure, the elasticity of the wall of these alveoli. And you need that surfactant in order to equalize the pressure. Otherwise, what happens is that the little alveoli collapse into the bigger ones. They'll, collapse, put the air in the bigger one, and then others go also in the bigger ones, and eventually the bigger ones rupture, and of course, you get catastrophic consequences. The book actually mentions that. 3, please tell us briefly what points of the reading you found most difficult or confusing. If you did not find any part of it difficult or confusing, tell us what parts you found most interesting. You need that second part there, right? Because you don't want students to write down, nothing is confusing, done, right? Okay. So let's look at 2 student answers. First student. Capillary action is due to the cohesion between water molecules and adhesion of water to the surface of the glass tube. That's correct, but it's actually a sentence just copied from the book and put in there. Negative pressures can result from the cohesive forces of water. Another sentence out of the book. I don't know what the relation is to the first sentence. But it's correct, but I can't follow the reasoning here. At the same height, the pressure inside the tube is much less due to negative pressure. I cannot follow the reasoning, but no matter what, it's wrong. Second question, the air flows from high pressure to low pressure. Good, that's correct. The fully blown up balloon has higher pressure than the half blown up balloon. Sorry, that's wrong. So the air flows from the fully blown balloon to the half filled balloon. Now look at the third question. Nothing was difficult or confusing. The sections on the surfactant in the lungs, question 2, were interesting, and the heart as a pump were interesting because they relate physics to biology. Okay, here's one example. Here's another example on the other extreme. The water rises because of an interaction between the water and the walls of the tube. This interaction creates an upward force which causes the water to rise. Incidentally, that is the same as the first sentence from the other. But instead of copying the text, the sentence out of the text, this student expresses it in his or her own words. The force is due to surface tension between the water and the walls of the tube. The pressure at the point inside the tube must be the same as the pressure at the point of equal height outside the tube, because if there was a pressure difference, there would be a net flow of water into or out of the tube until the pressure was equalized. Fantastic. Clearly, argued, correct, beautiful. 2, Laplace's law tells us that it requires a greater pressure difference to maintain a small sphere than a larger one. So the pressure in the small balloon must be greater, and the air will flow from the small balloon into the large one. Great. Now look at the third question. I found the explanation of Laplace's law to be inadequate. And while I can understand the conclusion drawn, I don't understand the reading which led to the conclusion. So I thought, what I really need to do is I need to code the questions 1 and 2, whether they're correct or incorrect. And then I need to hunt in question 3 for confusion expressed on the subject of these questions. So this one would be confused about question 2, Laplace's law, but not confused about capillarity, because he or she doesn't say anything about capillarity, but both correct. And this student here, not confused about either one, but wrong and wrong. So I did that for all 200 students, and then I analyzed the data. Of the students who said they were confused by capillarity, we've seen none of them, by the way, 44% got the question on capillarity correct. Of the students who did not say that they were confused about capillarity, 25% got it correct. What about Laplace's law? Same thing. Confused students, 49% correct. Not confused, 21% correct. Wait a minute. Are confused students twice as likely to be correct? What are the students who are not confused? They are students who have not even begun to understand because they haven't struggled with it. It's the same as going to a lecture, right? I am sure you must have had that. We have Friday lectures like this too, and I know I'm going a few minutes over time. I'm almost done here. But I go to a talk, and then an hour later, I walk in the corridor, and I come across a colleague who did not go to the talk, and he said, "Did you go to the seminar?" I said, "Yeah, I went. How was it?" "Oh, it's a brilliant seminar." "Really? What was it about?" And then all of a sudden you realize, well, it sounded brilliant, but I cannot reconstruct the argument. And I think the same is true for a lot of students just reading the text without thinking. So in later years, what we did is we changed the text to force the students to think. We put speed bumps in there. And when you force students to think during the reading, that difference actually goes away. Right? So what is the take-home message here? There's more confusion among students who understand, especially when they're not pushed to think. But here the important key point. Confusion does not correlate with understanding. Sometimes it even anti-correlates with it. And it's not necessarily, and I think this is the main point I want to make today, the result of poor teaching. When I taught my lectures, the students walked away happy, thinking everything was clear. They're taking their notes, everything sounded clear. Now when I teach with peer instruction, students keep asking questions. But what about this? But what about that? And it would be very easy to come to the conclusion, Eric, you're doing the wrong thing. But actually, I'm just, it's not enough to confuse them. You've got to get them beyond the confusion. But, at least they've taken the first step towards understanding, right? Otherwise, they walk away out of lecture with a false sense of illusion. Their brains, as those data from MIT showed, have not even been engaged. All right? So I think we need to recognize that confusion is part of the learning process. And unless we accept that, it's going to be very, very difficult to improve education. So I hope I've shown you how you can use your classroom to mine data that I think are very important to improve education. I want to acknowledge some of my co-workers. If you want a copy of this presentation, that's the URL. You don't need to write it down. Just go to Google, enter my last name, and then hit this I'm feeling lucky button, and then you'll have a copy. Thank you very much for your attention. Sorry for going over.
For those who can stay, we have time to take a few questions.
I'm curious about a textbook that's research-based and forces students to think, because I'm a high school teacher and I know that my students probably wouldn't read it.
They would what?
They would not read it. If it forced them to think too hard. So I'm just curious to know about whether you, like, I'm sure Harvard students will read it, but I'm just wondering about if it's too hard.
Well, I mean, you always have to adjust the pre-class assignment to whatever your students can do, right? You put the bar too high, and that's not going to work in any environment. And different environments are going to have different bars. So you have to find whatever balance. But even then, so the way the text that we use now works is, and the same is true is, you know, another thing you could do is you could send your students to watch the Khan Academy, right? Which many teachers do. But it would be good to intersperse, and Khan is starting to do that. I had dinner with him recently, and he showed me some of his new approaches. You know, you have a short video clip, and then you have a question, so that now you're not just watching and taking in information, you're trying out what you've just learned. You can do the same thing in a text. You have a few paragraphs, and then you have a question. Now, you could say most students can read over the question and continue, but this text is designed so that you cannot read over it because the text right after it refers to the answer of the question, right? So you have no choice. Well, you could look up the answer to the question at the end of the book, but you know, most people like solving puzzles, right? And would like to try it out, especially if there's no benefit to cheating, right? Because by nature, the human mind is curious. But I think if you use the Khan Academy, it's probably good to make sure that they answer the questions in between the different video clips in order to count on any meaningful preparation. You had a question.
Yes. I'm a graduate student, and I'm kind of curious if there is a difference in time for the two approaches, for the just lecturing versus your approach.
So the question is, by a graduate student here, are there perhaps different phases in I'm paraphrasing your question a little bit, are there different phases in people's educational development where lecture approach versus interactive teaching might be more beneficial? Step into any kindergarten, and you're not seeing anything like this, right? It's total chaos, it's playful, and that probably still holds through most of elementary school, right? Projects, activities, students working together. And then in middle school somewhere we transition to this completely passive approach of taking in things. After you graduate, hopefully soon, you will no longer learn in an environment like this. You'll be dependent on coworkers, on people around you, on self-directed study, things for which actually the lecture method prepares you very poorly, right? So I think that people in general learn by doing, not by listening. There's one exercise which I do always when I do a workshop. I ask people to take a little piece of paper and write down something they're really, really good at. Something they're proud of. It could be baking cakes. It could be solving partial differential equations. It could be interpreting medieval works of art. Anything. I want them to write that down. And then I ask them now, because you know the thing that you're good at, you usually enjoy, right? And also you know that others admire you for that. So most people have no trouble picking out something. And then I ask them, to write down in a few words how they became good at it. Now, and then you can see people get stumped. They don't realize how hard it is to think of things you like, how difficult it is to remember how you learned them, right? Because things you like, you learn more or less automatically. But anyway, as people write things down. And then, we often do this with clickers, I ask them to select different approaches and click in whatever is closest to what they wrote down. Most people have something like practice, typically around 60%. In general, less than 2% and often 0% selects lectures. Yeah, okay. I could show you the data. And I have thousands of data, and it's no different in China, from Chile to, you know, the Czech Republic, you name it, everywhere. It's the same. There are no cultural differences. We learn by doing, right? So I think having an oral transfer of information, having the professor write the book with his back or her back to you on the board is just not the way to learn. And it's, in fact, it's inexcusable to waste your time as a student, right, by having somebody transfer information to you, especially in an information age. So I think that it always pays off to be an active participant in the learning process rather than a passive recipient. Now, part of the problem, but that's a whole different subject, is the assessment, right? Because a lot of the assessment, I would say, is equally flawed. And I realized that the assessment that I used for many, many years really did not test any meaningful skills. Just as the lecture is a regurgitation of information to the students, so is the exam often a regurgitation of memorized information or of a procedure that has been memorized. In fact, we should really be testing skills that are more useful in life. So I've begun doing that, but that's for when I come back in a couple of years. One more question. Yes?
Your style of lecture or your style of teaching is completely different than what most students are used to. How much time and when do you spend on trying to explain to them why you're doing it differently and what the goal is? Middle, or beginning, or the end?
Yeah. You know, I'm glad you asked that question. Did everybody hear the question, or should I repeat it? It's about how much time, because my approach to teaching is so different, how much time do I spend justifying the method to my students? You know, when I first started teaching at Harvard, as I told you, I never asked myself, how am I going to teach? What was the question that came up in my mind? Put yourself in my position. You know, you're an assistant professor starting to teach, and you're told you're going to teach introductory physics. No, that didn't even come up. What? Or what book, right? So I went to a colleague, and he told me we use Halliday and Resnick. So I went to the Coop, ordered 150 copies of Halliday and Resnick, and as I went back to my office, I thought, wait a minute, if the students have the book and I have the same book, then what do I do in class? So I went to my colleague, and he said, oh, you know, don't worry, there are lots of books, and he showed me his whole collection, and I selected the perfect book for two reasons. One, it had a different approach. But the other reason for which it was the perfect book was, and which was much more important, was the book was out of print. The students couldn't get their hands on it. So I prepared these lecture notes to lecture from, right? And because the notes were different from the book, I decided to give a copy of the lecture notes to the students at the end of the class. Now, in retrospect, isn't that already admitting that there's a problem? But anyway, I didn't realize that. You know what the result was? At the end of the semester, about half a dozen students complained, Professor Mazur is lecturing straight from his lecture notes. Hello? You know, what was I supposed to do? Anyway, I tell my students this anecdote, and I've certainly completely gotten rid of that comment. And also, I show them some of the data, but I don't spend too much time justifying my method, because after all, they want to be sure that they can, you know, pass the MCAT and other tests that lay ahead. But they still do complain, no matter how much time I spend justifying the method. The nature of the complaints has very much changed. You know what they now write? Now they write, Professor Mazur is not teaching us anything. We have to learn it all ourselves.
I think that's a great place for us to end. Thanks very much, everyone.